I tell you a function is continuous on a set, what does that mean?
For all p in q, for all epsilon greater than 0, there exists delta greater than 0, such that for all x in u, if absolute value of x minus p is less than delta, then absolute value of f of x must have p is less than delta.
Cool. We agree? Right, because what is this? This is the same as saying for all p in the domain, f is continuous at that point p. Uniformly continuous. What's that mean?
For all epsilon greater than 0, there exists delta greater than 0, such that for all x in p in u, if absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon.
So all that moved is this. It wound up being declared at the same place as x. And the whole point of this, the difference between these, is what things that delta is allowed to depend on. In the definition of continuity, the value for delta is allowed to depend on epsilon and p. You can have different deltas depending on where you're checking for continuity. For a uniformly continuous function, you have to use the same delta no matter where you check for continuity. And we saw some examples last time, like 1 over x is continuous away from 0. It is not uniformly continuous. Because you get closer and closer to 0, you need better and better control over how close x has to be to p in order to get the same control over the difference between their output values. So we gave some examples of those. Let's talk about what uniformly continuous functions are good for, and I'll close with a little bit about compact sets. So let's start with what are uniformly continuous functions good for. So I'll state like what the main result that I'll hit in this particular subsection is. The key goal that I have right now is this theorem. Theorem 7.5.9. If u is a subset of R and f is a uniformly continuous function, then if you take any limit point of view, the limit of this uniformly continuous function as x approaches p exists. And that's not true for just continuous functions. Maybe I'll stick with the prototypical function of 1 over x. Y equals 1 over x. Does that have a limit as x approaches 0? Nope. Even if you allow for limits to be infinity, because it wants to be infinity and minus infinity. But 0 is a limit point of the domain. So this is exactly the type of badness that uniformly continuous things will avoid. And in order to prove that, I want to get a handle on sequences. So let's prove first the following result, which I think is nice. Here is a theorem. Let u be a subset of R, f be a function from R to R. If f is uniformly continuous, then for every Cauchy sequence of elements of the domain of f, the sequence f of xn is also Cauchy. So uniformly continuous functions take Cauchy sequences to Cauchy sequences. And I guess this should not be true for uniformly continuous functions. Let's try it for 1 over x. F of x equals 1 over x. Can you think of a Cauchy, aka convergent sequence, so that 1 over that sequence is no longer convergent? think about where the limit of such a thing would have to be. If this convergent sequence converged to somewhere in the domain of F, then like we have sequential continuity. So F of xn would have to converge to F of the limit of xn. So we don't want that. So we want a sequence that converges to a limit point of the domain that's not in the domain. What's the only limit point of this, the domain of this function that's not already in the domain? What's the only point not in the domain of this function? 0. And is there stuff in the domain that's really close to 0? Cool. So it looks like I want to try a sequence that converges to 0. Tell me a sequence that converges to 0.
1 over n.
Awesome. Good. Yeah, right, that's like a canonical one. If you're a computer scientist, maybe it's 1 over 2 to the n. So let's try it. Xn equal to 1 over n. For this function, what is f of that sequence? Is that Cauchy? No, it diverges to infinity. So this really is something about uniformly continuous functions. And let's prove it now. So let's let U be a subset of R. Let f from R to U to R be a function. U to R be a uniformly continuous function, right? Because that's one of the assumptions too. I need to show that for every Cauchy sequence xn of elements of U, f of xn is also Cauchy. So, what should I assume that xn is? Cauchy. If I want to prove this claim, I better assume the assumptions. And I guess just for the sake of grammatical correctness, it's a Cauchy sequence. What do I want to show? What's the conclusion of the theorem?
Fxn is a Cauchy sequence.
Radical. So, like, the guts are now going to happen. But I guess before we can even do those guts, let's remember what the word Cauchy means. What's it mean to be Cauchy? I don't know if I can use xn here, because xn has a jar that says f of xn. A.
Raw epsilon greater than 0. There's an n such that if m is greater than n,
Like that?
yeah, and little n is greater than n,
Okay.
then the absolute value of a of n minus j of n is less than epsilon.
Yeah. So it's the thing that's, unlike the definition of convergence, it doesn't say the terms of the sequence get close to a thing. It just says they get close to each other. That's what it means to be Cauchy. So we know what we need to prove. That's what we need to prove. We want to prove that claim? I guess we better start by considering any epsilon bigger than 0. And there's some like guidance in terms of steps here, but let's maybe go to the bottom and just try to like bullshit our way to a proof, and then we'll write it down. So, here's our goal. how can I get those two things to be close? Yeah.
Make x of m and x of m close to each other.
Where the delta is going to come from an appeal to the definition of uniform continuity. How can I get that?
Since x and is Cauchy.
So I can come up with a big N so that happens. Okay, cool. So it looks like my logic is going to be use this epsilon and uniform continuity to get a delta. Use that delta and the mod Cauchy to get a big N. Assume M and N are bigger than big N, then do this arrow, then do that arrow. Nice. In some sense, like, I think at this point you have the whole proof in your head, right? It's just a matter of putting it onto paper. Let's go through the motions. So I guess first let's get the delta using uniform continuity. Consider any epsilon bigger than 0. Since f is uniformly continuous, we see that well, maybe I'll start with this. Oh, yeah, sorry.
For all x p in u, if x absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon.
Nice. So like exactly that, but we've already declared the epsilon, so we don't need a for all epsilon, because we already have an epsilon in mind. As soon as you consider any epsilon bigger than 0, there probably shouldn't be any for all epsilon bigger than 0s until you get to the conclusion. Cool. So what's the next step? Use delta and Cauchy to get big N. So let's do that. This delta is bigger than 0, and xn is Cauchy. So I'm standing in the way of the definition of Cauchy. There's no place else to stand.
There exists n such that if n and n were greater than
Pen's a little faint. That pen is also faint.
then absolute value of xn minus xn is less than epsilon or less than delta.
Yeah, right. So we could put either an epsilon or a delta there, and that would be like not a false thing to say. But by looking at what the scratch work we have on the board, do we want an epsilon or a delta there? I think a delta. Awesome. Okay, things are coming together. So we considered any epsilon bigger than 0. We now have our choice of big N. Now we get to consider any little m and little n bigger than big N, and now we just push it forward. Since m and n are bigger than big N, the if-then in theorem 7.17 gives us a result. Those are both things in U, and they satisfy the if part of the if-then in 7.16. So I can get the then part of the if-then in 7.16. Does that do the job? Yeah, because what did we need to do? We wanted to show that f of xn was Cauchy. So we needed to show that for every epsilon bigger than 0, and there are like lines on the next page, but I've also got space right here. for every epsilon bigger than 0, so we considered any epsilon bigger than 0, we came up with the big N. There exists a big N such that we considered any m and n bigger than big N. The difference between the terms of the sequence is less than epsilon. Cool. That seemed pretty good. So, this is like a theorem of the form, if a function is Cauchy, then here's a thing that happens. You'll notice that this implication was written in one direction. I want to gauge people's intuition. Is this theorem actually an if and only if? And there's no judgment value on whether I agree or disagree. What's your intuition? Do you think that this seems likely to be true in the converse? Anyone want to say yes? Okay. Anyone thinks that it's likely to be false in the converse? Cool. I'm not going to tell you which. Prove or find a counterexample. This is now an unwritten challenge problem. If you want to do it. Once you know the proof or know a counterexample, it's not terribly hard to write up. So you know what you need to prove. Neato. Feel good? Next goal. Let U be a subset of R. F from U to R be a uniformly continuous function. Let P be a limit point of the domain U. Then the limit as x converges to P of f of x exists. And I guess with that challenge problem that I announced, I'm okay with being super vague with what you even prove or disprove. If you need to add some assumptions, add some assumptions. If you want to disprove something that's close to it, disprove something that's close to it. Let's prove this. So, this is a claim where I want to show that a limit exists. And we've done a few things like that when we talked about sequences. When we proved that if a sequence is Cauchy, then the limit exists. The overall structure was do some magic to come up with something like a candidate to be the limit. In this case, I think we defined lim suit basically. And then we showed that lim suit was actually the limit if you're Cauchy. That's not the only way to do it. We're going to do something similar here. Let's come up with a candidate to be the limit. And here's the strategy I'm going to use for that. So I'm going to take the limit at a limit point. Can I find a sequence that converges to that limit point? Will f of that sequence be convergent? Yeah, I guess by the thing we just proved, the sequence converges to the limit point, so it's Cauchy. So f of the sequence is Cauchy, so f of the sequence converges. So there's the strategy. We have that'll give us a candidate to be the limit. Then we have to prove that it actually converges to this thing. So let's try to do that. So let's start with getting the candidate. Let U be a subset of R. Let f from U to R be a uniformly continuous function. There was a version of this class in the distant past where I only considered functions whose domain is the whole real line just for simplicity. I didn't actually make anything simpler, but it screwed up the notes now. Let P be a limit point of the domain. I need to show that the limit as x approaches P of f of x exists. In order to come up with a candidate, I'll pass to the world of sequences so I can appeal to this theorem. So, since P is a limit point of U, there's a sequence xn of elements of U that are different from p, such that xn converges to p. All right, we proved that. If you have a limit point, that limit point is detected by the limit of a sequence. All right, so now let's do that. And maybe here I'll have you tell me what goes in the spaces. Since xn converges to p, what can I say about the sequence xn? It's Cauchy, because conversion can only in Cauchy. Since the sequence xn is Cauchy, the theorem we just proved lets us conclude that f of xn is also Cauchy. Well, since f of xn is Cauchy, what can I conclude about f of xn? Conversion. So this is like translating back and forth between the word Cauchy. Let's let y be the limit. So let's think about what this has proved. This proves that you have this nice uniformly continuous function. Here's this limit point p. I have the sequence xn getting close to p. I'll have a corresponding sequence f of xn. It gets close to some limiting value y. So I have a sequence of outputs so that the corresponding sequence of, a sequence of inputs so that the corresponding sequence of outputs gets close to p. If the limit of this sequence, this function exists, it has to be p. I see a bunch of inputs that get close to p, the outputs get close to y. So if the limit exists, that's the limit. So if I'm going to show the limit exists, I may as well show that the limit is y. Seem like a sensible strategy? Neato. In order to show that the limit exists, let us show that the limit is y. That's nice in that now we know what we actually want to prove. Ooh, let's remind ourselves what we want to prove. What's the definition of the limit?
For all epsilon greater than 0, there exists a big N.
Limit of a function, not limit of a sequence.
There exists a delta greater than 0. If x minus p is less than delta absolute value, then absolute value of fx minus f is less than 1.
I have only one addition I would like to make.
For all xn.
Oh yeah, I guess that too. That's not what I was worried about there. Oh, and this shouldn't be f of p, this should be y. I'm sure that the limit is y. So there's another change I would want to make. The limit doesn't care what the function does at p. Cool. We feel good? Here's what we want to prove. So let's try to prove it. And maybe again we'll try to come up with a picture of the proof first. I want that to be small. We're not small. So I think the strategy, though the way I'm going to try to come up with the proof, is try to come up with things that are close to other things. Do I have something that's close to y already? I guess I'll need n to be bigger than big N to do that. So if I knew that f of x was close to f of xn, that would make me happy. Can I get f of x to be close to xn somehow? Well, if I knew that like x minus xn were less than delta, I could do that. And I guess I can put any positive number I want there. Just need to show there as well. Oh wait, but can I get x minus x to be close to xn? So let's like move this off to the side. I want that to be small. Do I know something that's close to xn? P? Is P already supposed to be close to x? Yeah, because I'm taking the limit as x approaches P. Cool. So I think the overall strategy is going to be as follows. So use uniform continuity to come up with a choice of delta. Use Cauchiness to convince myself that x minus xn is small. That'll tell me that f of xn minus f of x is small. I can also use convergence to convince myself that f of xn is close to y, and then I can put those ingredients together. Seem coherent? And let's just, there's a lot of moving pieces there. So let's just make the progress we can. Let's start with the uniform continuity. Let's consider any epsilon bigger than 0. Since f is uniformly continuous, there is some delta bigger than 0, so that for all x in U, if absolute value of x minus p, nope, uniform continuity has 2 inputs for all x, and I better not use p, so let's give it a different name. For all x and a in the domain, if the absolute value of x minus a is less than delta, then absolute value of f of x minus f of a is less than epsilon. And in fact, I want to add some color coding. I want this to be epsilon, so I think I'm going to have to divide epsilon by something. At a glance, maybe 2. Maybe I'm not brave enough to decide what. Let's wait till we get to the end of the proof. We'll figure out what we need to divide epsilon by. It'll be something. So, let's do this. Let's consider any x in U. Let's assume that the absolute value of x minus p, let's see, these are like input values. So I think like, well, no. I want to, here's what I need to prove. I've put a for all epsilon bigger than 0. There's a choice of delta that comes from uniform continuity. I now get to assume that 0 is less than the absolute value of x minus p is less than any positive number I want. I'll put a delta in this space. I'll color code it green. And I don't know if that's going to be good enough to get all of the things I want to have happen at the end happen. But for now, I'll just say delta. If it doesn't work, then I'll see why it doesn't walk, and I'll be able to fix it. So, carrying on. We need to show that absolute value of f of x minus y is less than epsilon, because that's what I need to prove. All right, so let's do that. Xn converges to p. That means that there is some big N, so that for all little n bigger than big N1, I can make this difference as small as possible. And based on this picture, I think I want a delta there. Maybe even a delta over 2. Maybe I'm brave enough to divide this delta by 2. I think I'm not just yet. All right, so that means that the absolute value of xn minus x, whenever you have this game where like you know two things are close to the same thing, like you want the triangle inequality, right? And there was like a cross out and put the same thing back because I got myself scared that there was a typo there. There's a typo at the end. I don't think I wanted less than epsilon at the end. Absolute value of xn minus n. What's the thing that I know is simultaneously close to both of those things? P. In fact, let's jump straight to using the triangle inequality. Feel good right now? Do I have an upper bound on how big xn minus p is? Oh, from a mistake. That should just be an x, right? And I made that mistake in the non-erasable pen like a dummy. Xn minus p, though. Upper bound on that is? Yeah, that green delta, because little n is bigger than big N1. P minus x in absolute value is less than also delta. So now that I know that absolute value of xn minus x is small, I want to appeal to 7.18. To appeal to 7.18, I need the difference between two inputs to be less than delta. Do I have the difference between two inputs being less than delta? If I divide by 2, I do. So let's divide it by 2 for now. And if I need to divide by more, then I will divide by more later. So now that I know the absolute value of xn minus x is less than delta, at least as long as little n is bigger than big N1, we conclude that absolute value of f of xn minus f of x is less than epsilon, and at this point my inability to stick with a single color coding scheme is coming back to bite me. I wanted the red epsilons to be the things that I might have to divide by something eventually. So I'll just put a line underneath that to make sure I know that I might need to divide that epsilon by something. So right now I have f of xn minus f of x is small. There's this edge in that diagram. Feel good right now? All right. Now I still need f of xn to be close to y. Why is f of xn getting close to y? Yeah, but that came from, N1 came from the wrong place. N1 came from xn goes to p. There's going to be another n. There's going to be an n2. F of xn goes to y. So there's some second big N, which satisfies that for all little n bigger than big N2, absolute value of f of xn minus y is less than an epsilon that has a line underneath it because it might need to be divided by something. Things starting to shape up? All right, so the eventual goal is y and f of x are close. Right now, do we have something that is simultaneously close to y and to f of x? So what's like the tool you use to now say that y is close to f of x? Triangle inequality? Nice. And I'm beginning to feel confident that I want to divide my epsilons by 2. I don't know if I'm 100% confident, but I have erasable pen, so I guess I could. All right, so let's write down the assumptions. So it looks like I had 2 different choices of big N floating around. Let's assume little n is bigger than both of them, so I can appeal to both of those lines. Then, absolute value of f of x minus y is the same thing as absolute value of f of x minus f of xn plus f of xn minus y. And I guess I added and subtracted f of xn there. Appealed to the triangle inequality. And now let's just walk out what this is less than. Do I know f of x minus f of xn is less than something? I know f of x minus f of xn is less than epsilon. And let's just check that that lines up with the since part. The line that says absolute value of f of x minus f of xn does not need little n to be bigger than big N1 or big N2. Big N1. Okay, cool. So that's in the right place. Since little n is bigger than big N2, what do I get to conclude is smaller than epsilon? Nice. So that is less than epsilon. Oh, cool. So maybe I'll put this right here. Epsilon plus epsilon. That's 2 epsilon. So are you walking out the divide by 2 is the right thing? Cool. So let's go back to the beginning of the proof and fix it. So uniform continuity says that there is some delta such that if x and a are in the domain and the are close to each other, then I can make f of x minus f of a to be as close as I want them to be. I can put an epsilon over 2 there. It follows then that this just used 7.18. That was less than epsilon over 2. F of xn goes to y, so I could put any positive number I want there. That could be epsilon over 2. And now I'm set up on the next page. Thus, absolute value of f of x minus y is less than epsilon. Is that exactly what I needed to complete the proof? So here's like a neat thing to observe here. There are a bunch of like n's that showed up in the middle of the proof. Are they actually part of the statement or conclusion whatsoever? No. So there are different ways to prove this that don't go through studying the sequence. But if you're going to study a sequence, you're probably going to have some n's. Fair enough? Nice. So with a few minutes left, is there enough time to make progress here? Let's see what progress we make. So we have a good reason to want to think about uniformly continuous things. In that if you have a uniformly continuous function, then it's going to, you can take limits wherever you want. There's no danger about you're at a place where you can't take a limit. There will be no vertical asymptotes. Basically, most bad behaviors that continuous functions can have, they won't have Unless you want to start talking about like derivatives and stuff, which you might want to at some point, but we won't in this class. Let's prove this. So if you have if you have a compact set and a continuous function on that compact set, then it is automatically uniformly continuous. So what this says is as long as your domain is compact, so just a closed bounded set, continuity automatically upgrades to uniform continuity. And the proof of this is going to follow a model that will really, I think, nicely illustrate why the definition of compact is what it is. What are we going to do? We're going to take the assumptions, turn the assumption into an open cover, use compactness to say, oh, here's a finite subcover, use the finiteness of that subcover to come up with our delta. So let's do that. So let's let C be a compact set. Let's let f from C to R be continuous. We need to show that f is uniformly continuous. The strategy is use continuity to get an open cover. Take a finite subcover of that cover, which we know we can by compactness. That subcover will tell us the choice of delta to use for absolutely every x. So let's do that. We'll consider any epsilon bigger than 0. That's now the epsilon that I'll use for the rest of the proof. Let's let A be in C. Since this function f is continuous at A, there's some delta that depends on the choice of A. And so I'm going to call it delta of A, which satisfies the definition of continuity. For all x in U, if absolute value of x minus A is less than delta, then absolute value of f of x minus f of A is less than epsilon. And this, like, we've seen this sort of weird notation where I say, well, this delta depends on something, so I'll encode the dependency in the notation. Like, there's nothing magic about it, but it lets you do some kind of powerful things in that that gets me an open cover. So think of this delta as being a function from U to positive real numbers. Here is an open cover. Let's define mathcal f, squiggly f, to be the set of all things that look like A minus delta over 2 to A plus delta over 2, where A is in this compact set. Is that obviously an open cover? Is every element of it obviously open? Open intervals are open, so yes. Is everything in the set obviously in one of those? Yeah, let's convince ourselves of that. Let's consider any A in C. I need to show A is in some element of squiggly f. Which element would you expect A to be in? How about the one that involves A? Yeah.
Say delta equals
Not delta equals A, but I'll use this A. Then A is an element of A minus delta of A over 2, A plus delta of A over 2, which is in mathcal f. So every element of C is in some element of this collection of open sets, so it's an open cover. And I've got 4 minutes left. This is a compact set, and I have an open cover of this compact set. What just should the next line be?
finite subcover.
There's a finite subcover. That's the definition of compactness. Whenever you get an open cover of a compact set, there is a finite subcover. And so this is what I mean when I say compactness lets you turn infinitely many open conditions into finitely many. Each of these A's has a different delta associated with it. That's like infinitely many conditions. I can get down to just finitely many. By compactness, there is an open subcover. Call it U. And so that U is now just a list of, I guess, n many things that are elements of MathCal F. I don't know how many there are. There could be a billion, there could be 6. Point is, there are finitely many. Cool. So here's what should make you feel good about this. I now have finitely many choices of delta to use. Whenever you have like 2 choices of delta, like when you want to add together continuous functions to get a continuous function, you take the min, right? If I take the min of those n many deltas, do I get a positive number? Is it now independent of which x I chose? Ooh, that's the game. So let's let delta be the min of all of those things divided by 2. Notice I haven't told you why division by 2 is a good idea yet. Like certainly there's nothing wrong with dividing by 2, but it's not clear why to do that. That hopefully will become clear in the next 2 minutes. So let's see, I started by considering any epsilon bigger than 0. There's my choice of delta. I've come up with a choice of delta. Now I need to consider any 2 things in the domain. On the board they're called x and p, but what's in a name? Let's assume that the absolute value of x minus y is less than delta, which I should. I need to show that the absolute value of f of x minus f of y is less than epsilon. And I'll do it by using these a's. So this sucker is an open cover. So that means x has to be in one of these things. Buy that? Cool. That means the absolute value of x minus ai is less than delta of ai over 2, which is less than, I guess, just delta of ai. Does that mean f of x is close to f of ai? Yeah. By the way, we define these deltas. These deltas were chosen so that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus f of a is less than delta. Where that delta is depends on the choice of a. Cool. F of x minus f of ai is less than epsilon. The reason I divided by 2 is so I can also compute the distance from y to ai. Y minus ai is less than or equal to Do you agree with that? Y minus x is by assumption less than this delta, which is the min of a bunch of things. So it's less than each and every one of them. X minus ai, yeah, that's less than delta over 2. So the difference is less than just delta. That's why I divided by 2, so that I wouldn't have an extra 2 here. Oh, but now I think I'm about to get myself into trouble again, because f of x minus f of y is now less than or equal to f of x minus f of ai plus f of ai minus y. Is that less than epsilon? I mean, almost, right? What is this piece less than? This piece is less than? That's 2 epsilon. Oh, is this like now a standard trick to fix the proof? Cool. So, I'm past time by 2 minutes, so I'm going to stop. I'm not going to add anything more. What do you think? Could you now fix the proof in like 2 seconds on your own? Yeah, throw some division by 2s in there. Make sure they're in the right place. And this is a standard trick you'll see used in a lot of analysis papers. Like they'll wind up at the end of the proof saying, oh, and this is less than 2 pi divided by 3 times epsilon. And then they'll just stop. Because they'll say, well, at this point, anyone reading this paper knows that I should have just divided my epsilon by something. In a lot of math papers, there are enough hard constants to understand that are floating around that they don't introduce them at the beginning, even though they know they'll need them. Cool. I hope everyone enjoys their Thanksgiving. At the very least, I hope you manage to rest.
Good Thanksgiving.
You too.